Okay, recording has started. To those who are going to watch the recording later, we started the lecture about 6 minutes ago. We started 9.4 types of collision, and I forgot to click on the record button. All right. So each one of these. So I'll skip now to slides, and then we can come back to this. So your book says things one way. I started using the book's terminology. I am going to continue using the book's terminology, but I am also going to use some other types of terminologies. And then towards the end of the section, we are going to merge them all together. Okay. Let's take the example of billiards. Okay. I'm going to reopen the okay. Let's take the example of billiards. Okay. One ball hits another. It stops. Sorry, Ryan, say that again. Okay.
I said شطرنج. I meant
Okay.
billiard.
No problem. Okay. So here's the example of billiards. The orange ball moves with some velocity, hits the purple one. Now here's a key component. After hitting it, the orange ball stops and the purple ball starts moving. Okay. How do we analyze the situation? Okay. When we have a collision, okay, in which no external forces to the system act, so we define the system in this example to be, for example, the two balls. Okay. Momentum is conserved. Momentum before the collision is equal to momentum after the collision, which is what we have already explained in the previous lecture. Okay. We start with many to many. Okay. And then we will go back to many to one. Okay. So in many to many collisions, okay, we have different types of collisions. We have elastic collisions where kinetic energy is conserved. We have inelastic collisions where some kinetic energy is not conserved. And we have completely inelastic where after the collision, the objects stick to each other. So what I will do is I will, so that we have them all in one sheet. Look at this. And also, this. Okay. Now, yes, no? Nope. Okay. All right. Let's bring these terminologies all together so that going forward, we know exactly what we are going to be talking about. Okay. We have a collision. Two things just hit each other. Okay. If the final kinetic energy is somewhere between 0 and the initial kinetic energy, okay, we call it an inelastic collision. Kinetic energy after is less than kinetic energy before. If the final kinetic energy is 0, so something happens and then it stops, we get 0. Okay, let me see. Okay, can we try again now? Is now clear? What is cutting off, the sound or the video?
Sound.
Okay. Okay. I've disconnected pretty much everything from the internet except my laptop. Hopefully, it will improve. Okay. Okay. So we have momentum. Okay. Momentum is always conserved. Okay. P is always conserved. We also have kinetic energy, which before we used, okay, or actually we have energy, which before we used to say that it is always conserved. Okay, now this is very important and I'm going to write it in red. Energy total is always conserved. Kinetic energy is not always conserved. So what are the options that we have? We have bodies that are colliding with each other, okay? Momentum before is equal to momentum after all times. If kinetic before is equal to kinetic after, we call it an elastic collision. Okay, you can remember it like an elastic band. Okay, you pull it, it goes back to exactly how it was. If some of the kinetic energy, okay, is not conserved, so say for example, there's friction, there is heat, your kinetic energy is a little bit lost somewhere, we call it an inelastic collision. If after the collision, the final kinetic energy is 0, okay, we call it perfectly or completely inelastic. Okay. Now this leaves us with one option. What if our final kinetic energy is more than initial kinetic energy? I started with 100 joules of kinetic energy, or 0 joules of kinetic energy, for example, and I ended with 2000 joules. What is that? That is what we call an explosion, and hence I have written boom in capitals. Okay, is my voice still cutting off?
واضح واضح يا دكتور ما قطع.
Okay, perfect. All right. Let's look at them in one dimension, one at a time. Okay, so one dimension, first we started with inelastic collisions. Okay. We agree that total momentum is conserved, so Pi equals Pf. We have one body hitting the other body. Body 1 has mass 1 and velocity 1. Body 2 has mass 2 and velocity 2. What happens when they hit each other? Well, afterwards, since this is a many-to-many collisions, they are still both moving, but one of them, crap. This is bad. Okay. ما لابس سماعة كنت وبعدين شليتها الحين. No, upload and download are both solid. Sorry, it appears the problem is from your side, not here. Yeah, sorry, it appears the problem is from your side, not from mine. Okay, so we started with two masses, m1, m2, with two different velocity, v1, v2. We ended up still with two masses and with two different velocities. This is 9.4. Okay, but your book doesn't present it in a logical way. I'm trying to present it as logically as humanly possible. Okay, so P1 plus P2 before equals P1 plus P2 after, which means M1 V1 plus M2 V2 equals M1 V1 plus M2 V2. Do you agree with this so far? Okay. Now, bear in mind, this is only momentum. Okay. Energy might not all be equal. For example, in the case of a billiard ball, when one ball hits the other, we hear a sound, clack. That sound carries away some of the energy. So even though our momentum is conserved, if we look at only the kinetic energy, okay, it might not be conserved because we lose some of the energy as sound. Okay. Let's take a look at a different example. Same two balls, but this time there's something different. Take a look. Once it finishes hitting, they stick to each other and they both move together. How would our equation change? Before, we had two masses and two different velocities. One of them was moving at some velocity, the other one was stationary. And afterwards, the two masses are now one mass together, and they have only one velocity together. So how would the equation be? We would end up with m1 v1 equals m1 plus m2 v. Can you hear me? Someone written وين راح الدكتور? This is very confusing. Oh, okay, perfect. Okay, so to write it in full form, okay, we had m1 v1 plus m2 v2 equals both of them together, m1 plus m2 v final. Now, because our v2 initial is 0, this goes to 0. Okay? All right. This is just for completely inelastic. Okay? So, this is for elastic inelastic. No, it could be different. I'll give you an example in a second. This one is if completely inelastic. And why do you ask a very good question? Does it always have to be 0? No. Let's do an example. We will have m1 v1, then we will have m2 v2. After collision, boom, we have them both together going at v3. Now, in this case, our equation will be m1 v1 plus m2 v2 equals m1 plus m2 v3. This does not go to 0. If initially it's 0, we can put this as 0. If not, then not. Okay. Depends on the situation. Okay, I will skip this and I will come back to it later because we have not done this center of mass yet. Let's look at elastic collisions in one dimension. Okay. If the collision is elastic, and this is especially in a special case, our total kinetic energy before is equal to the total kinetic energy after. And so is momentum. Okay. So if something is moving, we have m1, m2, m1 v1, m2 v2 equals m1 v1 plus m2 v2. This is pi equals pf. And we also have for the kinetic energy initial equal kinetic energy final. Let's look at examples. Okay. You can rearrange this equation in a billion different ways, okay, and get V1F as the subject, V1I as the subject, V2I as the subject, V2F as the subject, and so on and so forth. No, you do not memorize these, and I cannot say this enough. Do not memorize this. Understand this. Okay? There is no point in memorizing these bunch. Okay. Let's take one example. Two bodies, one is stationary, one is moving. They hit each other. Now both of them are moving. I'll play it again. What is our equation going to be now? Initially, we have M1, M2. V1 is something. V2 is 0. It's not moving. Later on, we have M1, M2, and both of them are moving with different velocities. Our momentum is going to be conserved. M1 V1 equals M1 V1F plus M2 V2F. Our kinetic energy is also going to be conserved. And now we are here considering a very ideal collision. Okay, an elastic one. Some of you might be confused. لأنه قبل شوية I said the sound caused by the clunking of the balls loses some energy. In real life, yes, the sound will make it lose some energy. At the moment, we are considering not real life, but an absolutely idealistic version. Okay. You can rearrange them. Let's take an example. Let's take special cases and see how these play out. Say we have equal masses. Now, if M1 equals M2, what happens if they are both the exact same mass? I will take these equations and I will rewrite them here again. Okay. Take a look. If M1 equals M2, what happens to V1F and what happens to V2F? V1F ends up becoming 0 because if M1 equals M2, then M1 minus M2 will be 0. So this whole thing will be 0. V2F will simply be equal to Vi, the same. So this is a very simple case. You have something coming in at 10 meters per second, hitting something stationary. The stationary thing is going to move at 10 meters per second, and the thing that was initially moving is not going to move at all. Okay. What about this case? You have a very tiny ball hitting a very big ball. Now, just without physics, just from you knowing and playing around with stuff in your childhood, what's going to happen here? Anyone? It will move back. The small one will go back. Yes, exactly. And we are going to prove it using physics, conservation of momentum. This is what we call a massive target. Your target is way bigger than your source. Okay. M2 is way more than M1. So if M2 is way more than M1, okay, Let's do it. M2 is way bigger than M1. M1 minus M2 is going to be almost just minus M2. M1 plus M2 is going to be almost just M2, right? Times V1I. So this is just simply minus V1I. So V1 final is minus V1I. What does that mean? It means it's the same number, but in the opposite direction, which is what 3 of you already said. It will move back. What about V2 final? V2 final, okay, we have 2M1 at the top, M1 plus M2 at the bottom. Since M2 is much, much bigger than M1, this is pretty much saying this is only M2, V1I, and M1 over M2, if M2 is much, much bigger, will be very, very small number, maybe even 0.
Doctor, can you repeat it in case 2 in V2? The case in V2 final.
V2 final. For V2 final, here you have 2M1. We take 2M1 just here. صح? Good. Now I have M1 plus M2. If M1 is just 1 kilogram and M2 is 1,000 kilograms, okay, what's M1 plus M2? 1001. 1001 is almost the same as 1000 as an approximation. You don't really make a big difference, do you?
Yes.
Okay. So you end up with a very small number. Okay, you end up with 2M1 over M2 V1I. Let's take an example with numericals to make it clearer. Say M1 is 1 kg. M2 is equal to 1000 kg. V1I is equal to 10 meters per second, which is quite a fast ball. Okay. 2 M1 over M1 plus M2 times this. What is our answer going to be? 20 divided by 1001, it's 0.02 meters per second. It's a very, very tiny amount. Okay. What about the opposite? Say, for example, I have a huge ball coming in to hit the tiny, tiny ball. So my M1 is way more than M2. What will I end up with now? Both of them are going to move. Excellent. With what velocities? The same velocity of the big one. Let's try it out. And let's try it out with some numbers and see what we get. Okay. Let's use the same numbers. M1 is one. Let's use the same number. M1 is 1000. M2 is 1 kilo. V1 is equal to 10. V1F, so the big ball, will be 1000 minus 1 over 1000 plus 1 times 10, which is equal to 9.9 something. 9.98. Which is almost 10 meters per second. Okay, so almost the same. But what about the small ball? The small ball started with the small ball was stationary. Okay, so V2F will be equal to 2 times M1, the big ball, which is 1000, over mass of big ball plus small ball times this. And what is the answer here now? This is something we usually don't expect. $19.98, which is approximately 20, which means this is twice velocity of big ball. It's double. And you can imagine this is real, and you know it is real, but you haven't really thought of it in terms of physics before. Can you imagine when you are walking down the road nicely, and if someone really, really big or fat bumped into you from behind? You don't simply end up walking together. What happens is you feel a push and you very quickly go to the front. Right? So what happens is, okay, so what happens is you actually gain twice the speed of whomever pushed you from behind, which is why you end up stumbling. Okay, so this is it in terms of conservation of momentum. What if M1 penetrate M2 and then move together? If M1 penetrates M2, then M2 no longer exists because it will shatter into tiny pieces. But if M1 sticks to M2 and they move together, okay, then you will go back to the case of the inelastic collision, or the totally inelastic collision, which is this. Okay, so if we do it, where's the whiteboard? Pi equals Pf. Okay, so if something is moving M1 V1, something else is moving M2 V2, and then they become together and move as one, M1 plus M2 V3, we will end up having M1 V1 plus M2 V2 is equal to M1 plus M2 V3. Now it depends, Azan. Was the first ball moving beforehand or not? Let's assume it was moving. Okay, let's assume it was moving, and we will use the exact same numbers. So V3 will be equal to M1 V1 over M1 plus M2 plus M2 V2 over M1 plus M2. Let's put in some numbers. We agreed that the big ball coming in was 1000 and the small one was 1 kilo. So 1000 times 10 meters per second over 1000 plus 1 plus 1 kilo times, I will also have it move at 10 meters per second initially, divided by 1000 plus 1. What is my V3 going to be? This is 9.99 plus which is approximately 9.99. So they will, so what will happen is both of them will end up moving together with the velocity of the bigger ball, because the smaller ball is going to be overwhelmed. There's not much that it can be that it can do. Okay, let's see if we have understood this. Ball 1 hits a stationary ball 2 in one-dimension elastic collision. The initial momentum of ball 1 is P1I, and the final momentum of ball 2 is P2F. And they are both shown here. P1I is 4 units, P2F is 5 units. What is the magnitude of the x component of P1F? Okay, someone said 1 maybe. Remember, it's asking for the magnitude, not the actual number. Okay, so the correct answer is 1, and I'm going to tell you how, and it's much easier than you think. We agree that Pi equals Pf, right? What is the total initial momentum? Ball 2 is stationary, so velocity is 0, so its momentum is 0. So Pi is equal to 4 units total. We know the final momentum of P2 is plus 5, and we don't know what is P1F. The only way the left-hand side is equal to the right-hand side if P1F is equal to minus 1. Right? Minus 1 plus 5 is equal to 4. Now, since the question asks for the magnitude of minus 1 is equal to 1. And hence the correct answer is 1. Okay. Let's try another one. A big ball of mass 10 m, speed v, strikes a small ball, mass m, at rest. Could the following occur? Is it possible or not? The big ball comes to a complete stop, and the small ball moves with the speed of 10v. Is it possible or is it not possible? Yes, this can occur. No, it cannot, because it would violate momentum conservation. No, it cannot, because it would violate conservation of energy. So you need to try both of them. Okay, one person said yes, it can occur. A couple of people are saying no because it would violate momentum. Okay. Interesting. Pretty much everyone says A or B, but believe it or not, the correct answer is actually C. Why? Let's first look at conservation of momentum. Pi equals Pf. Initially, we will have m1 v1 plus m2 v2 equals m1 v1 plus m2 v2. So, mass of this first thing is 10m. Its velocity is v, so 10 mv. v2 is stationary, so this goes to 0. Now this goes to 0, and we will have m 10v. So we have 10 mv equals 10 mv. So this is good. Conservation of momentum is done. So it cannot be this one because momentum is conserved. Let's check energy. Kinetic energy initial equals kinetic energy final. Let's see. Initially, we have half 10m v squared, right? At the end, we will have half m, but the velocity is now 10v squared. This will end up being 5 mv squared. This will become 50 mv squared. I will take the v squareds away, the m's away, and we will get 5 equals 50. Is this possible? This is not possible. So this cannot occur because it would violate conservation of energy. Now, what if it was the other way around? What if it was 50 goes to 5, not 5 goes to 50? Would it then be possible using conservation of energy? See, if it was 50 to 5 in theory, then it would be okay because our kinetic energy got reduced. Yes? So it lost it due to friction, due to heat, due to sound. It's an inelastic collision. But if the momentum is conserved and the kinetic energy is reduced, that's fine. It's an inelastic collision. Our problem here is the energy seems to increase by a factor of 10 from 5 to 50. Yeah? Now, if it reduces, we say, okay, there was a collision and, something happened and it lost energy, sound, heat, friction. But there is no reason why in a collision, the energy content would increase. It makes no sense. It makes absolutely no sense for that to happen. Okay? So it's not possible because it would violate the conservation of energy. Okay. Let's move to 9.5, collisions in multiple dimensions. Well, even if it's a collision, Azan, we still use the conservation of energy because energy has to conserve at all times, even if it's a collision. Okay. Al-Ayham, actually, it is not possible. Okay, in an Indian film, maybe. Okay, but in other places, no. Okay, because conservation of energy and conservation of momentum are two universal laws. Okay, so what happens is you need to check that neither law is violated. Okay, it's like saying you have two laws. My car cannot move without petrol, and my car cannot move if it does not have any tires. Okay, so we have two conditions. My car needs to have petrol, my car needs to have tires. Now, just because my car has tires does not mean it has petrol. And just because my car has petrol does not mean it has tires. Okay, both conditions need to be satisfied for the car to move. And it's the same thing, conservation of energy and conservation of momentum, okay, need to both be satisfied. As we saw in this example, okay, and I've chosen this example on purpose, as we saw, it can be that momentum is conserved, but energy is not conserved. So for this to happen, you need somehow to magically invent 10 times the energy. Where did it come from? By definition, a collision, okay, conservation of momentum in a collision only involves internal forces within the collision itself. And if we don't have external forces, then we cannot get extra energy. Yes, we can lose energy. That's why we have the class of inelastic collisions. That is fine, but we cannot gain energy for no reason. Okay, hopefully that is now a bit clearer. Now, your book actually has some very, very nice thing about the Thomson model and the Rutherford model on page 431, which I will try to come back to if we have time. But first, let's do an example on collisions in multiple dimensions. Now, before I do this, I have been hearing I've been receiving and speaking to multiple students who have a very, very valid point, which I would like to address for a minute. They say, and I'll switch to Arabic, okay, دكتور المحاضرة مفهومة، المسائل اللي نحلها في المحاضرة والأمثلة اللي نشوفها في المحاضرة أيضا مفهومة، لكن لما نجي نحل في الكتاب نشوف أشياء تدور الرأس. الأمثلة اللي في الكتاب تدور الرأس. Okay, and you have a very valid point. And one of the reasons this is because many, many questions in your book depend on calculus. And we have a problem because, unfortunately, Calculus 1 is not a prerequisite for this course, which means we have so many of you who are coming to this course who heavily uses calculus, but you haven't actually studied calculus yet. And that is a very big, big problem. Okay. So the only thing I can say is the reason I don't do all the book problems in the lecture is because first I need to get the point across. I need to get the idea across. Okay, and then in tutorials or in office hours or after the lecture, we can do more problems. Okay, but there's no point in doing very complicated problems if we don't get the idea first. Okay. Now, collisions in 2 dimensions. We'll take 9.8 away so it doesn't confuse you, because in your book, this is actually 9.5. Okay. Let's take the example of a glancing collision. You have M2 here in the center, and a particle is coming from V1, hits it at the corner, and then it continues in this direction. Okay. Now, this type of collision, although in 2 dimensions, still, or even if we go to 3 dimensions, it still has to conserve both momentum and energy and total energy. It might or might not conserve kinetic energy, but it still needs to conserve total momentum and kinetic energy, momentum and total energy. Okay. In this case, we will take a simple example that actually conserves both of them. Okay. So it hits it, and what happens is ball M1 goes down at an angle θ1, and ball M2 goes up to V2. This is something typical that you see in billiard or snooker all the time. Okay. How do we solve this problem? We solve this problem exactly the same way we solved problems in chapters 3 and 4 when we had to do motion in 2 dimensions, and exactly the same way we did it in chapters 5 and 6 where we did forces in 2 dimensions. Okay. Now for momentum, since it's also a vector, we also do it x alone, y alone, x and y never interact. So we first start with kinetic energy. The total kinetic energy before is equal to the total kinetic energy after. Exactly. We do it with components. Give me a second. Okay, so since the ball 2 initially is not moving, it does not have kinetic energy, so that goes to 0. We have half mv squared before equals half mv squared after plus half mv squared after. Simple, no problems here. We do the same with momentum. Okay, but remember, momentum is a vector, so we take it components x and y. In x, we have m1 v1, it's only coming in x, we don't need sines or cosines, is equal to m1 vf cosine theta plus m2 v2 cosine theta. In y, we don't have anything in y in momentum because it's only coming in x before. And later on, we will have minus m1 v1 f sine theta because it's going down, so minus, plus m2 v2 sine theta. So what we did is we just took the components of both of them. Now we have 3 sets of equations and we can solve for whatever on earth we want to. Let's take this. Actually, do we have time? Yes, we have a couple more minutes and a few. Okay, let's do this. Ball 1 strikes stationary ball 2 in a 2-dimensional elastic collision. The initial momentum of ball 1 is P1I, 4-0. And the final momentum of ball 2 is P2F, 3-2. What is the component, x component of P1F? Excellent. Everyone figured out 1. This is 4. This is 3, which means the difference is 1. Good job. Now, what if I asked you about the y component? What is the y component of P1F? The y component, not the magnitude of the y component. Careful. I did not ask for the magnitude. Excellent. Most of you got it right. P2F has a +2 y component, which means this will need to have -2, and this will be its direction. Okay, you can see it graphically. Okay, you can see it graphically. Since initially you had 0, nothing, your final needs to be 0. So if one of you has +2, the other one needs to have -2, so that the total is still 0. Excellent. Well done. So in theory, we have covered 9.1, 9.4, and 9.5 today. That leaves us with 9.6 and 9.7 for the next lecture. Unfortunately, we took longer than anticipated today for momentum, but I honestly don't mind that because it is very, very crucial that we understand the concept of momentum. Okay, we can call it a day. Okay. Yes, Shema, up to 9.5. Yes. Okay. So I'll stop the recording because the lecture has ended.